Extrusion and liquid based processes. So, in rapid prototyping we had solid processes, then we have liquid based processes wherein which you can use a liquid and then convert it into a solid, or you take a solid, convert it into a viscoelastic state and then make a solid to get the required prototype output. So, this topic we will see extrusion and liquid based processes. Extrusion process means you are trying to take a wire which will be extruded through a nozzle, wherein which the wire from a solid state would get converted to viscoelastic state, and then it will be laid on top of a table, and then you keep on be repeating it and then decreasing the Z. So, you will try to get a full complete solid. So, extrusion is one process, and the stereolithography we saw some basics, that will be a liquid based processes. In this chapter we will see introduction, basic principles, plotting and path control, different types of materials, which is very important because the entire rapid prototyping process depends upon the basic starting material. And today when we talk about rapid manufacturing, we are talking about directly producing the prototype and using it in the real time applications. For example, tissue printing is something which is more talked about today. It is a polymer, starting material is a polymer, and then you make the composition of the polymer to such an extent that you can try to print tissues, and these tissues can be interfaced into the body and it becomes a original part over a period of time. Then limitations of FDM process, bio-extrusion and the other systems we will try to see in this lecture. Extrusion based technologies can be visualized as similar to cake icing. In cake icing what we do is we try to have a cake, and then in this cake top we always give a topping wherein which we write, suppose it is happy birthday, right. So, when we wanted to write this, what we do is we use a cone, okay. This cone is filled with icing whatever it is, and then this is allowed to fall by, and here this hopper whatever we had, this is allowed to move in XY direction, and when we generally what we do is we use our hand, and inside the hopper what we have is all icing material, that is sugar powder which is mixed with some butter or something which is in a very viscoelastic state. It is not a solid state, it is a viscoelastic state such that you apply a very small pressure, move your hand in left and right direction whatever it is and start writing your name. So, if you look at it, it is lot of flexibility is there in your hand. So, you can even tilt it to whatever you require, and at some places you want to stop, some places you want to give second line coating, it is possible. But however, please understand, when you try to compare it with this cake icing, it is more dominated towards 2.5D structure. That means to say the D height will be few millimeter, you can't go few inches in that, okay. So, generally what we do is for easy understanding we try to give an analogy of cake icing. So, in the material contained in the reservoir is forced out through a nozzle when the pressure is applied. If the pressure remains constant, then the resulting extrusion material, commonly referred as rod, because when you start pushing it and draw a line, this H, this is called the rod, will follow at a constant rate. Suppose you run very fast, when you try to put the rod, when you try to run very fast, there can be discontinuity in the line, or there can be a lump mass at the start, at the end, and in between you will have a thin line coming up. So, if they are extruded at a constant pressure, then you will get a rod width and height uniform, will flow at a constant rate and will remain a constant cross section diameter. This diameter will remain constant if the travel of the nozzle across the deposited surface is also kept at a constant speed. If we try to draw a line and if we try to do it very fast, maybe then you will have this type of when there is a difference in the flow or in the pressure you might get discrete lines, or you might get a lump mass, then small, and then you will have. So, this lump mass will form a, will get thinned down over a period of time, and then this will try to thicken, and then you will try to get something like this. So, this is also because of varying pressure and varying feed rates, that is the speed with which it moves, right. The material that is being extruded must be in a semi-solid state. Go back to this icing example, and please remember this icing, cake icing, which is very good analogy. So, if it has become solid, then you can't push through the nozzle, or if it becomes solid, you have to apply lot of pressure to push through the nozzle. When it becomes a solid and when you try to apply lot of pressure, there can be a discontinuity in the flow even. Say for example, when the flow happens like this, you can have discontinuity in the flow which comes out of the nozzle. This is the nozzle. When it becomes a solid. So, it is always a basic understanding to keep in mind that you should use a semi-solid state and then push it through the nozzle, try to maintain a constant speed and try to maintain a constant pressure. Okay. The material must fully solidify when remain in that shape. Further, the material must bond to the material that has already been extruded so that a solid structure can result. For example, you have made a H. If the width of the H, whatever you have made, suppose let us assume you wanted to make a line like this. And when you make one pass through the nozzle, you get only one line. Now, what you are supposed to do is you will go back and you will start putting the next line. So, what I am trying to say is, if there is a discontinuity, or if these two lines do not join, if these two roads do not join, then you will not be able to get a proper adhesion between these two roads. This will try to bring in discontinuity. It might give you a very poor look. So, this also should be kept in mind, that there should be an overlapping, or when the overlap happens, there should be a sticking between the two roads. If I try to draw the cross section, it will be like this. Okay, there has to be something like this. So, this will only make sure that there is a proper bond of material that is already extruded. So, this is first and this is second. If this fellow dries it off, then sticking will be a problem. So, you should make sure that this fellow does not dry, and this fellow when it joins, it should have a phenomena of sticking. This is only in one layer I am talking, but if you want to construct a 3D object, then it should be between layers also there has to be a sticking happening. So, what has been extruded and what is getting extruded should join and form a solid. Keep that in mind. This is very important. If this does not happen, there is a phenomena called as delamination. This delamination will make the prototype look very poor, and this cannot be used further. Since material is extruded, the rapid manufacturing machine must be capable of scanning in a horizontal plane as well as starting and stopping the flow of the material while scanning. So, for example, you started from here, the H beginning, this is the start point and this is the end point, and you finished here. If you wanted to reuse from here, you can start from this side itself and go, otherwise you go all the way on the top and start from there. So, that is what they say, must be capable of scanning in the horizontal plane as well as start and stopping of the flow of the material while scanning. Once a layer is completed, the machine must index upward or move the part downward so that the further layer can be produced. So, if this is what is the H, we are moving in one plane. Happy birthday, what you write as H is just a single layer. Suppose let us assume that you wanted to make a 3-dimensional H. So, if I wanted to draw the plan view of it, suppose let us assume it is going to take, this is first layer, second layer, third layer. Okay. So, these are the two legs of the H. So these are the 3 layers. So then what we are trying to say is either this fellow should sink, the table should sink, or the nozzle whatever is there, that fellow should go up, so that it tries to create the layer. There are 2 primary approaches when using an extrusion process. The most commonly used approach is to use temperature as a way of controlling the material state. So what I am trying to say is, you have already extruded one layer, and this layer, when it is exposed to the atmosphere at certain temperature, it will try to solidify. So if I have to slow down the solidification process, then what I do is I use an ambience around it and try to maintain a temperature in the ambience. When I start maintaining the temperature in the ambience, then the extruded layer and the just extruded layer will try to join with each other and form a layer or a road completely in a plane. Molten material is liquefied inside a reservoir so that it can flow out through the nozzle and bond with the adjacent material before solidifying. Okay. So now I think you should be able to appreciate, when you look into the analogy of icing and when you look at rapid manufacturing extrusion process, it is almost the same. This approach is similar to conventional powder extrusion process, except the extruder is vertically mounted on a plotting system rather than remaining in a fixed horizontal position. An alternative approach is to use a chemical change to cause the solidification. Chemical change is what? Already you have a liquid, you apply either a chemical you add in it, or you apply a initiating agent. For example, you can apply a light which hits at a polymer, and the polymer has a curing cycle catalyst inside it, it cures. So that is what is a chemical approach. In such a case, the curing agent, residual solvent, reaction with air, or simply drying of a wet material permits bonding to occur. This process is stereolithography. Okay. Parts may therefore cure or dry out to become a fully stable. This approach may be more applicable to biochemical applications, where material must have a biocompatibility with living cell, and so choice of material is very restricted. This is more bio applications. However, industrial applications may also exist, perhaps using a reaction injection molding related process rather than relying entirely on a thermal effect. This is also possible. Reaction injection, we will see that in due course of time. So there are a number of key features that are common to any extrusion based process: loading of material, liquefaction of material, application of pressure, extrusion, plotting according to the predefined path in a controlled manner, bonding of material to itself or a secondary built material to form a coherent solid structure, inclusion of supporting structure to enable complex geometry features. Supporting structure, suppose I told you last class itself, if you have a free hanging body, so this free hanging body will be done by a supporting structure. Okay. So these are all the common key features which are to be thought of when we talk about extrusion process. These will be considered in separate sections to fully understand the intricacies of extrusion based rapid manufacturing process. So this is a basic principle for FDM process, fused deposition method, FDM process. So here we try to take a filament wire which is polymer. Generally what we use is ABS. ABS, nylon can be used. Okay. So people are now working on various systems. You can also have biocompatible material. ABS is also biocompatible ABS is there, industrial ABS is there. You can choose any of them. Choose a polymer. Why polymer? Polymer solid. It goes into viscoelastic and then it becomes a solid once again. So it does not go to a liquid state. So here you apply heat. Okay. So viscoelastic means you take it to a shape such that you can try to give a shape to the solid. It is in a semi cured form. Okay. So that is what it is. So filament is there, polymer is you can also use metals. Today we are talking about metals, where people are trying to use copper, aluminium, steel, Okay, steel rods are used, they are passed through a nozzle. Okay, so in order to have a proper tension, constant pressure of feeding, we use this pinch roller. This is for constant pressure. You remember in the cake icing example, we talked about constant pressure. So these two pinch rollers try to give a proper tension to the wire such that the wire moves inside the nozzle. And when we are talking about polymer, what we do is when the wire is passed through the nozzle, it is heated. So when it is heated, it goes to a viscoelastic state. So this is done in the liquefied chamber. So this is a heating, completely heating will happen here. Okay, heating also you do not take it to a liquid temperature, you increase it to some 50, 60 or 100 degrees Celsius. By 100, 120 degrees Celsius you just heat, and then the polymer is passed through. And now what is happening through the nozzle tip? So here it can get bulged, right? This can get bulged or this can get deformed, whatever it is, but when it is pushed through a constant orifice, that is the nozzle tip. So what you get out is a constant diameter. And now what you do is you try to move the table in x direction and y direction, so you get a single layer. And once the platform is pulled down by one layer thickness, then in the z direction you try to construct an object. So the object is called a scaffold. So please keep the analogy of icing and then start doing it. So here the feed rates, the constant laying feed rates are dictated by the table movement. So there has to be a synchronization between the pressure with which it exits out or the way it exits out and the speed in order to get a uniform rod thickness. A mathematical understanding of extrusion process can quickly become complex since it can involve many non-linear terms, extrusion process, and second thing, it is a polymer. The starting material is a polymer, so you have lot of non-linear terms. The basic science involves extrusion of highly viscous material through a nozzle. It is reasonable to assume that the material flows as a Newtonian fluid, which is not correct. It is a non-Newtonian, polymer always is a non-Newtonian fluid, but we assume that the shear stress versus shear strain follows a linear trend, Newtonian fluid in most cases. Most of the discussion in this section we will assume that the extrusion of a molten material and may therefore include temperature terms. For solidification, these terms are generally expressed relative to time, and so temperature could replace by another time dependent factor to describe curing or drying process. So you see here we are trying to take time, so temperature would be replaced by time dependent factor. So we have laid down all the common features. So material loading is one. Since extrusion is used, there must be a chamber from which the material is to be extruded. So generally what happens, if you look at the nozzle, we will try to have this nozzle will be attached to a spool. This spool will be continuously, and in the spool we will have something like 1000 meters long wires which is passed through it. Okay. So it is passed through it, we will pass and get it. Since extrusion is used, there must be a chamber from which the material is extruded. Here it is a wire, so you put it in a spool. If you do not have a spool, if you go back to your icing example, it is a huge, above the nozzle you should have a hopper. So that is what is a chamber. This would be preloaded with material, but it will be more useful if there was a continuous supply of material into the chamber. If the material is in the liquid form, then the ideal approach is to pump the material. Most bulk material is, however, supplied as a solid, and the most suitable method of supplying are in pellet or powder form, or where the material is fed in as a continuous filament. So this you can have it in pellet, you can have it in powder, you can have it in continuous. If you take injection molding, it is pellet. Okay. If you try to take pellet or otherwise called as powder form. So, in injection molding where extrusion is done, we use this. The chamber itself is therefore the main location for the liquefaction process, which I said there is a heater applied. Pellets, granules or powders are fed through the chamber under the gravity or with the aid of a screw. Liquefaction. The extrusion method works on the principle that what is held in the chamber will become a liquid that can eventually be pushed through a die or a nozzle. As mentioned earlier, this material could be in the form of a solution that will quickly solidify following the extrusion, but more likely this material will be a liquid because of heat applied to the chamber. Such heat would normally be applied by heater coil wrapped around the chamber, and ideally this heating should be applied to maintain a constant temperature in the melt. The extrusion, finally first is loading, then heating, then extrusion nozzle determines the shape and the size of the extruded filament, because what comes out will be a liquid in terms of we call it as a continuous one, so that is a filament. Okay, the shape and size is decided by the nozzle orifice. You can have a nozzle orifice like this. For example, when you talk about birthday, we have orifices of the nozzle coming like star. Okay, you can also have oblong, you can also have slits. Okay, the shape and the size, this is all nozzle exit shape. Okay. The shape and the size of the extruded filament depends on the nozzle exit diameter. The large nozzle diameter will enable material to flow more rapidly, but would result in a part with low precision compared with the original CAD drawing. So, the diameter of the nozzle dia is an important factor for deciding the accuracy of the part. The diameter of the nozzle also determines the minimum feature size that can be created. No feature can be smaller than the diameter, and in practice features should normally be large relative to the nozzle diameter to faithfully reproduce them with satisfactory strength. So, no feature can be smaller than the diameter, can be diameter of the nozzle diameter. Okay, this is also an important point. Extrusion pressure processes are therefore more suitable for larger parts that have features and wall thicknesses that are at least twice the nominal diameter of the extrusion nozzle. This is a thumb rule which you should understand. So, the wall thickness that are at least twice the nominal diameter of the extruded nozzle used. So, when we talk about extrusion, using a simple screw geometry, molten material will gradually move along the screw. This is for injection molding channel towards the end of the screw where the nozzle is velocity W of the material flow along the channel is given as W is nothing but pi into D into N. D is the screw diameter, N is the RPM with which it does, and the screw angle. So, for example, you have a screw, this screw will be this screw angle we are talking about. Okay. The velocity of the material U towards the nozzle is therefore given by this, and this is the velocity W of the material flow along the channel, it is this way. So, these two velocities are different. W is the material flow along the channel, this is velocity of the material U towards the nozzle. Okay. So, here now comes an interesting thought process. See, from the pellets, these are pellets or powders, whatever, polymer powders. From the pellets you get converted into a wire. This is a wire. This wire is used in FDM process. By the process called extrusion, we try to make a output. Now people have started thinking, why should I use pellets to convert wire and then wire, extrude them and use it in FDM? Rather than that, why don't I bypass this step and directly go from here to here? So, the starting material for FDM today, people are thinking, why don't we use pellets itself? So, this will reduce one process, and here when we start using pellets and go directly to FDM, the resolution of the objects can be improved. So, people have started directly using these pellets instead of the spool feeding nozzle and other things. You will have a hopper which is used in injection molding machine, hopper, then a screw. The pellets will be asked to pass through the screw and it will be exit out through the nozzle, and then it will lay on the table. So, this is another process. Here people have started working. Why? Because to improve the resolution of the FDM, because if you use a wire, there is always a restriction in the feature resolution. So, the extrusion for a constant helical angle, the volumetric flow caused by the screw in the barrel, known as a drag flow QD, is proportional to the screw dimension and the speed. So, constant helic drag force. So, the drag forces with which it resists to flow. Since we are operating under drag flow, the relative velocity of the molten material will be W for the material that is in contact with the screw, and 0 for the material in contact with the stationary wall of the barrel. So, we must therefore integrate over the height of the screw and try to get the QD. So, QD, the generalized molten material travelling down this rectangular channel, the along channel flow QD through the channel of B width and dy is the height can be expressed in integrating from 0 to h WB dy. So, which is nothing but W into B into h by 2, where h is the screw depth. W by 2 is defined as the mean down channel velocity. Substituting back in the QD, you get this equation. So, here we assume there is no friction, it is first principle, generalized one, we get it. We must now consider pressure flow in the channel. Flow through a slit channel, width of L, height is h, and infinite length can be derived from the following fundamental equation of shear stress tau. Tau is nothing but dP by L, okay, where x is the perpendicular to the flow direction and dP is the pressure change, pressure drop along the diameter, and L is the length. So, for a Newtonian fluid it is defined like this. So, it is minus viscosity eta into dVz by dx. So, where eta is nothing but the dynamic viscosity of the molten flow defined by the Newtonian fluid. Combining these previous two equations, we have this is the final equation. From here you can try to find out the eta value and try to substitute it in the equation. The next one is going to be, till now hopper, flowing we saw. Next one is solidification. Why solidification? It will lead to delamination. You want to avoid delamination. So, we have to focus on solidification. Once the material is extruded, it should ideally remain the same shape and size. The gravity and surface tension, polymer material, gravity, surface tension, however, may cause the material to change shape, while size may vary according to cooling and drying effect. If the material is extruded in the form of a gel, the material may shrink upon drying, as well as possible becoming porous. So, for this, what I would suggest is you do an exercise using your toothpaste. You have bristles, you have your brush, okay. So, on top of it you try to place the paste. And note down the diameter, plot the diameter change with respect to time. You see that the diameter will keep reducing with respect to time. This is because of the viscoelastic behavior. So, that is what the gravity, surface tension, however, may cause the material to change shape, while size may vary according to cooling and drying. If the material is extruded in the form of gel, it can shrink. What happens? The diameter will reduce, but it is a constant volume process. So, this diameter will become this diameter. The height will reduce because it is a constant volume. If the height will reduce, the diameter will increase, that is all. If the material is extruded in the molten state, it may also shrink when cooling. Okay. On top of it, shrinkage is cooling is also there. The cooling is also very likely to be non-linear. If the nonlinear effect is significant, then it is possible the resulting part will distort upon cooling. So, you should keep this signs in mind when we do the process. The solidification rate, the shear rate can be, the gamma dot can be expressed as dV by dr, and the shear stress can be expressed in tau, where m represents the flow exponent and phi represents the fluidity. The general flow characteristics of the material and its deviation from the Newtonian behavior is reflected in the flow exponent m. So, this takes care. Then the next one is the position control. Position control is either you move the nozzle in xy plane or you move the table in xy plane, right. For example, if the extrusion head is moving at a velocity v parallel to the nominal x direction and is then required to describe a right angle so that it moves at the same velocity v in the perpendicular y direction. So, I am just saying, if the extrusion head is moving with a velocity v, parallel to the nominal axis x. So, this is your x plane, and is then required to describe a right angle so that it can move at the same velocity v in the perpendicular direction as y direction. Okay. At some point the instant velocity will reach 0, because you have drawn a line completely and then you stop, then you take a diversion. So, that is what they say, at some point the instantaneous velocity will reach 0. If the extrusion rate is not 0 at that point, then excess material will be deposited at the corner of this right angled feature. So, what they are trying to say is, if you are trying to make some feature like this, at this point you will have a large deposit of material. Since the requirement is to move a mechanical extrusion head in the horizontal plane, then the most appropriate mechanism to use would be standard planar plotting system. So, standard planar plotting system. This would involve two orthogonal mounted linear drive mechanism like belt driven or lead screw. Normally, in all the FDM process where the resolutions are not high, resolutions are low, we use belt drive. When the resolutions are very high, then we use lead screw. But keep in mind, it is also depending on the nozzle diameter. See, if the nozzle diameter is large, you put a lead screw of a very high precision, what you get out will be a low feature. So, there has to be a trade off between these two. Okay. Since the requirement is move a mechanical extrusion head in the horizontal plane, then the most appropriate mechanism to be used would be the standard planar plotting system. Plotting system uses a belt drive. You have a timer pulley and a belt drive. Position control. Now you have moved. The next thing is position control. The internal filling pattern can be built more rapidly since the outline represents the external feature of the part that corresponds to the geometric position. So, what we are trying to say, you had a layer, okay. This is a layer and this is the internal filling. This is the external and this is internal filling. Okay. The internal filling pattern, so these are the roads what we talked about, these are the roads, okay, can be built more rapidly since the outline represents, correct. Now, so this is what is the precise control required. Internal, if you can, it's just to fill material. So, the internal fill pattern can be built more rapidly, no control, since the outline represents the external feature of the part that corresponds to the geometric position. This outer shell also represents a constraining region that will prevent the filler material from affecting the overall precision. A typical fill pattern can be seen. So, this is the external feature and this is the internal fill. So, we can see here, this is a pattern, this is a pattern and this is a pattern, this top one is a pattern. a position control, a typical fill pattern using an extrusion based system created in 3 stages. One is filling vertical, right, the other one fill pattern is at an angle, and the third one is along the different angle. So, this is the along a straight line. The next key feature is the bonding. As I told you, delamination will come. For heat based system, there must be sufficient residual heat energy to activate the surface of the adjacent region, causing bonding. So, you have 1, you have 2, so you maintain it under a temperature. This is a chamber, temperature chamber. So, there is sufficient enough to activate and bond. Alternatively, gelled based system must contain residual solvent or wetting agent in the extruded filament to ensure the new material will bond. It is just like a glue stick paper, you have glue put on the top and then you have a paper. So, that is something like that. Wetting agent in the extruded filament to ensure the new material will bond to the adjacent region that have already been deposited. In both cases, we visualize the process in terms of energy supplied to the material by extrusion head. If there is insufficient energy, the region may adhere, but there would be a distinct boundary between new and previously deposited material. This defect is called as delamination. This can represent a fracture surface where the material can be easily separated. Too much energy may cause the previous deposited material to flow, which in turn may result in poorly defined material. So, if you make the temperature very high, then this fellow will be in also viscoelastic, this fellow will be also viscoelastic. So, it will be very poor surface will be there. Support generation, this I was trying to tell you, you have a free hanging surface. This free hanging surface has to be supported. For example, if you want to make an object like this, okay. So, this fellow has to be supported from here. This is called as supporting material, which will not be the same as the original material. So, inside this you will have rods and lay, whatever it is, pattern. This is a fill pattern. The supporting material or the structure, whatever it is, does not play a role in the final product. All RM systems must have a means of supporting freestanding and disconnected features, and for keeping all features of the part in place during the fabrication process. With extrusion based system, such features must be kept in place by the additional fabrication of supports. Support in such system take 2 general forms: similar material support or secondary material support. Similar material, what will happen is the density of the material fill will be low, so that it can be easily broken off. Secondary is that the strength of the material itself, the strength of material is low. So, here you will have 2 nozzles, okay, 2 nozzles to feed. If an extrusion based system is built in the simplest possible way, then it will have only one extrusion chamber. If it has only one chamber, then support must be made using the same material as the part. The support generation, this may require parts and support to be carefully designed and placed with respect to each other, so that they can be separated at later time. If it is continuous of the supporting material and the original material, then it is going to be very difficult. As mentioned earlier, adjustment of the temperature of the part material relative to the adjacent material can result in a fracture surface effect. This fracture surface can be used as a means of separating the support from the part material. So, what are we trying to do? We are trying to make a crack or a cleavage. So that the cleavage can be easy, that initiating crack, this will easily propagate further, it will break down and it will fall down. These fracture surface may be used as a means of separating support from the part. One possible way to achieve this may be to change the layer separation distance when depositing the material on top and supporting material vice versa. For example, that is what I said, the density you can change. Additional distance can affect the energy transfer sufficiently to result in the fracture phenomena. So, plotting and the path control. So, path control is start stop, this is start stop. So, how do we do it, and then how do we come back, serpentile pattern, or we just go like this, this is start, this is stop. So, these are some of the patterns, plotting and path control. As with nearly all rapid manufacturing system, extrusion based machines mostly take input from the CAD system using generic STL file format. The file format enables easy extraction of the slice profile, giving the outline of each slice, layer by layer slice. As with most systems, the control software must also determine how to fill the material with the outline. This is particularly crucial to this type of system. However, since extrusion head physically deposit material that fill previously vacant surface. This is particularly crucial to this type of system. However, since extrusion heads physically deposit material that fills previously vacant space, there must be a clear access for the extrusion head to deposit fill material within the outline without compromising the material that has already been laid down. Additionally, if the material is not laid down close enough to the adjacent material, it will not bond effectively. In contrast, laser based system can permit and in fact generally require a significant amount of overlap from one scan to the next, and thus there are no head collusion or overfilling equivalent phenomena. One spot, the other spot, this is a laser spot. Part accuracy is maintained by plotting the outline material first, which will then act as a constrained region for the filling material. So, external will be filled and then you go for internal. The outline would generally be plotted with a lower speed to ensure consistency material flow. So, this will be slow speed. The outline is determined by extracting intersections between the plane and the triangles in the STL file. These intersections are then ordered so that they can form a complete continuous curve for each outline. There may be any number of these curves, either separate or nested inside of each other depending upon the geometry of that cross section. So, filling, we are talking more about this filling which is happening inside. So, the extrusion of material to maximize precision left and maximize strength in the right. So, this is the outer boundary. This is the inner fill. So, you can see here maximum precision. So, you can see it is on the left hand side and this is stitching. So, you can see the outer and then this is done. So, you can see actual tool path will be this, deposited material boundary will be this. So, it is just like your cutter. In your milling cutter, what we do? We write the entire program to the center of the cutter. Okay, and this is the diameter offset which is done. Same way here, you write the program to this dotted lines, and what gets generated will be the solid lines. So, plotting and path control, it can be seen that precision control of the extrusion is a complex trade-off dependent on a significant number of parameters: input pressure, temperature, nozzle diameter. So, temperature again nozzle temperature and the chamber temperature, nozzle and chamber. Material characteristics, polymer, crystalline, amorphous, and you have partial crystalline. All these fellows have a direct influence on the mechanical property and the physical property, gravity and other factors, temperature built in within the part. These are some of the key features which depend on plotting and the path control. Input pressure, this variable is changed regularly during a build, as it is tightly coupled with the other input control parameters. Changing the input pressure applied to the material results in a corresponding output flow rate change. A number of other parameters, however, also affects the flow of the to a lesser degree, but pressure is very important. This is what you have to go back to your cake icing. Temperature, maintaining a constant temperature within the melt inside the chamber would be the ideal situation. However, small fluctuations are inevitable and will cause change in the flow characteristics. This can be because of clogging, this can be because of the material property, there can be a small fluctuations or the supply. Temperature sensing should be carried out somewhere within the chamber, and therefore a loosely coupled parameter can be included in the control model for the input feed pressure to compensate the temperature variation. So basically what are we trying to do is we are trying to add one more source which tries to maintain temperature variation. Okay. So we add a coupler, or we add one more sink, whatever it is, or we add one more source to make sure. As the heat built up, the pressure should drop slightly. As the heat is built up, the pressure should drop. So P should drop slightly to maintain the constant flow, because if you give more pressure, more flow rate will be there. So you have to have a trade-off. Nozzle diameter, we have already seen, is a constant for a particular build, but many extruder based systems do not allow interchangeable nozzles. What you buy in the market today which is available, you always get with a constant nozzle diameter. Very rarely they give, because when we try to change the diameter, what happens is if you don't properly fit in the nozzle, so you will not get the part whatever you require, and this needs little bit of expertise. So it is all custom made, you get only one diameter nozzle. The material characteristics I have told you in plenty. This would include viscosity information that would help in understanding the material flow through the nozzle. Since viscous flow, creep, etc. are very difficult to predict, accurate starting and stopping flow can be very difficult. So you start here. When you start here, it will be pressure, temperature, you have to monitor, and then it drops down. Along the line, again you have to withdraw back, right? This is start, this is end, withdraw back. So this is very difficult. Starting and stopping of the flow is difficult. Gravity and other factor, if no pressure is applied to the chamber, it is possible that the material will still flow due to the mass of the molten material within the chamber, causing a pressure head. So by gravity itself it droops down. Like for example, when you try to close the tap, if sometimes you see after you close also there will be 1 or 2 drops coming out. That's basically because of the gravity. So if no pressure is applied to the chamber, if it is possible that the material will still flow due to the mass of the molten material within the chamber. This may also be exacerbated by gaseous pressure built up inside the chamber if it is sealed. The surface tension of the melt and the drag force of the internal surface of the nozzle may retract this effect. So we use these things as an advantage for stopping the gravity flow. The temperature built in within the part, all parts will start to cool down as soon as the material comes out of the extrusion. However, different geometries will cool at different rates, because it depends on surface to volume ratio. If there is a large surface and the height is this is height, okay, and this is height and this is dia, fine. So the same thing I can draw it like this, same material. So, the surface to volume ratio is high here, surface to volume ratio is low here. Okay. So, that is what we are trying to say. However, different geometries will cool at different rates. Large massive structure will hold their heat for longer time, right, surface to volume ratio low, than smaller thin parts due to variation in surface to volume ratio. Since this may have an effect on the surrounding environment, it may also affect the machine control. So, this fellow might cool very fast. When it cools very fast, it also distorts very fast. So, that is what we are trying to tell here. So, the limitation of FDM, generally all nozzles are circular and therefore, it is impossible to draw sharp external corners. So, we can't get a nozzle orifice like this, we always get orifice like this. So, these are dead centers wherein which the flow will not happen. So, we do not go for square nozzles. Internal corners and edges will also exhibit rounding because of dead center. The actual shape produced is dependent on the nozzle, acceleration and deceleration characteristics and the viscoelastic behavior of the material as it solidifies. The speed of an FDM system is reliant on the feed rate and the plotting speed. Feed rate is also dependent on the ability of supply of material and the rate at which the liquefier can melt the material and feed it through the nozzle. These are all the limitations. If the liquefier were modified to increase the material flow rate, most likely it would result in an increase in the mass flow. So, please make a note of all these things. These are the limitations. This in turn would make it more difficult to move the extrusion head faster. For precise movement, the plotting system is normally constructed using lead screw. This is what I told you. The low cost system will always have belt because here the accuracies are not there, but flexing in the belt make it less accurate and this is also a lower torque reduction to the drive motor. One method to improve the speed of the motor drive system is to reduce the corresponding friction. So, we go for polymer timer belts. By gliding the head of a cushion of air counterbalanced against the magnetic force attracting the head to a steel pattern, friction was significantly reduced, making it easier to move the head around at a higher speed. So, this is to reduce the friction. So, one method not tried out the research labs as yet is the use of a particular build strategy that attempts to balance the speed by using a thicker layers with the precision of using thinner layers. So, it is still in research lab. Okay. The concept here is that the thin layer only needs to be used on the exterior of the part, thin layer on the exterior of the part. The outline of the part can therefore be built in with thin layers, but the interior can be built more quickly with thick layers. Okay. So, now the state of the art is they use same road diameter, road width. Since most FDM machines have two extrusion heads, it is possible that one head could be of a thicker nozzle, the other one thinner, so varying diameter nozzle. This thicker nozzle may be employed to build support and thinner for the external support. However, the difficulty in maintaining a correct registration between the two layer thickness has probably prevented this approach for being developed commercially.